So we've had some experience how to do this before. If I wanted to write 1/2 times 4 to the 5th into my calculator, right, I would take some parentheses and I'd do the 1 divided by 2 part, right, and then I'd hit the multiplication symbol, and then I'd hit 4, and I'd use that little up arrow symbol to the 5th power. Also, what works on your particular class set of calculators is you can do 1 and then that ABC button, 2, and if you're doing a fraction, that's going to look like on your calculator, I believe 1, something like that on your calculator. So that's another way you can enter in fractions. Again, if I was typing this in my calculator, I'd do 6 times parentheses 2 divided by 3, close parentheses, and then I'd up arrow to the 6th. Or, right, I would do the 2/3 using that ABC button, which is basically your fraction key. So with that in mind, now you should be able to enter in your calculator the values for basically all these different things. So if x is -2, or x is -1, or x is 0, or x is 1, or x is 2, right, it's going to be 1/2 times 4 to the -2. And 1/2 times 4 to the -1, and 1/2 times 4 to the 0, 1/2 times 4 to the 1, 1/2 times 4 squared. Right, and in all of these, you can use your calculator to literally do 1 divided by 2, comma, multiply 4, and then the up arrow, right, and whatever term for x that's supposed to go, like in the first example, it's -2, but the very next one, right, whatever's supposed to go there. So hopefully that makes sense. And then you're going to get some number figures. And for this one, it's going to be like 0.03125. Let me erase that because it's wrong. 3125. There you go. And it's, you're going to kill me. You write it correctly, 0.03125. And the next one, 0.125. The one after that, 0.5. So it looks like it's definitely getting larger. And that's an ordered pair, right? That's the 0.28, 1, 2, 0, 0.5, -1, -1, 0.125, and -2, 0.03125. And the graph of that, right, is, well, 1, 2 is right there, and 2, 8 is right there, and then you have 0 and 0.5, that's like right in there, and then -1 and something like really teeny tiny, -2, even tinier. So I'll give you another moment to write that down, and then I'm going to move on to the next example. Going further down in our examples, if our domain, remember domain are just all the x values. So -1, 0, 1, 2, 3, and 4. And the formula is 6 times 2/3 to the x power. And then I just plug in a -1. So it's going to be 6 times, essentially in parentheses, 2 divided by 3, up arrow, -1. And then 6 times 2 divided by 3 in parentheses, up arrow, 0. And then 6, 2, right, you get the point after this. This stuff here is what I'm typing in the calculator. And for the 2/3, you can also use your fraction key, and you'll wind up with the same stuff. So when you do that, that gives you numerical answers for all these, and you get something like 9, 6, 4, 2.6. With that little symbol above, it just means it's repeating decimal, 2 2/3. 1.7 repeating decimal, and approximately. And this symbol, right? This symbol simply means, approximately. .19, something like that. And of course, these are actual points on the graph. -1, 0, 6, 1, 4, 2, 2.6, 3, 1.7, 4, 1.19, about. So if I actually graph this thing, this one would start like way up here, and then down to here, and then down to here, somewhere in there. And so on. So you can kind of see the general shape that it's taking. So from here, we're going to move on to the next page. Writing an equation for an exponential function. So we have basically the exponential function is f of x is equal to a times b to the x. And we, by finding or calculating the values of a and b. So the value of a is the value of the function when x is equal to 0. So this would be, in other words, it's basically our initial value. Or when we were doing sequences, right, what was f of 1 when we were doing sequences? Right, this is like basically the first number in a sequence. But now that we're out of sequences, the initial value, right, is basically when x is 0. So another way to think of this is also the y-intercept. The y-intercept of an exponential function. And the value of b is the common ratio, something that does carry over from sequences. The common ratio of the successive function values. So b is always equal to basically f of x plus 1 divided by f of x. And in your sequence examples, right, when we took basically f of 2, divided it by f of 1, that gave us our common ratio also. So you'll see there's a lot of similarities in exponential functions and geometric sequences. So we're going to stop the guided notes there, and then we're going to move on to the homework packet.